as I said before, this is what I'm going to show is a linear model of the basilar membrane, and this is called a gamma tone filter bank. And this is a filter bank consisting, or maybe how it's described is described as a set of filters, because a filter bank is not a single filter, but a certain set of filters working simultaneously. And it's first introduced as a time continuous linear filter, and then it's transferred to a time discrete system, which can be then implemented in an actual computer model, let's say. So it is a set of time continuous filters, and as you can imagine from what we saw before, it is a set of bandpass filters. So that for each frequency we have a filter which covers the which represents the frequency response around that corresponding point, so that it matches well with the auditory system, or gives a good approximation of it. Because of that, you can select, because it's bandpass filters, you can select first the frequency spacing. And this is most frequently, as I mentioned before, with gamma tone filters selected to be proportional to the ERB, or to the ERB number scale, I would have to say, to that scale where ERBs are equally wide. And then the bandwidth of the filters should be selected as the ERB at those center frequencies. But now, why are they called gamma tone filters? This comes from the design of the impulse responses, because they are generated as modulations of a certain envelope. That means you will see it on the examples later. There's and the shapes of these envelopes are corresponding to functions you would know from gamma distributions, and that's why they are called gamma tone filters. And that's when you have specified the parameters in the time continuous case. You can approximate them as digital filters with time discrete systems. Yeah, gamma tone filter bank. So you have a set of bandpass filters, all operating on the input signal, because you want to know how certain vibration at the input would influence the vibration at different positions of the basilar membrane, corresponding to the outputs of the individual filters. And so you would have this set of filters. And this would be the time continuous case, and then this would be approximated with time discrete filters. And now coming to the gamma distributions, if there would be a probability density of a gamma distribution, you have different parameters. You have x would be the variable, but then you have k is kind of an order. That means you can have gamma functions or gamma distributions of different orders, and then you have the variance. And by the order and the variance, you can specify the gamma distribution. And I plotted here different distributions for different parameters for different orders, 1, 2, 3, 4, again 4, but 4, and then with 2 different variances. And you see that if the order is 1, then this is constant, because you have x to the 0, this is 1, and you have here a to the minus x divided by theta, and then this is just a constant again, because it just depends on k, not on x, and this as well. So this would be just an exponential function. So it always starts, depending on how you normalize it, but you would have to normalize it that the area below the curve is 1, because else it wouldn't be a probability distribution density function. So, and that's why here it would, in this case, with a variance of 2, it would start at 0.5, and this would be the orange line. And if you have a second order, k is equal to 2, it would not start from a value which is non-zero, but it would always start out of 0. But it could start with with a certain slope directly going out of 0 here. Yeah. So that's, you can see in the example of the black line. And the higher the order, you multiply here polynomial of x. You can imagine the flatter the curve gets out of 0 and then bends up to go up. And that's how the order influences the total shape. And in practice for gamma tone filters, there's often an order of 4 used. So the curves would have shapes like that one or the green one and so on. And so that would be the first part, to use some of those functions. And then you generate an impulse response out of that. And now this is a bit simpler description. You don't have this gamma function. The gamma function is here only used for, or only required for normalization, so that it gets a distribution. There you need this gamma function. But if you you can normalize that separately, then you don't need to write it here directly. But you can say, well, there's an amplitude factor A, then you have, instead of x, you have t, because it's a time continuous impulse response. You have A times t to the power of k minus 1. This would be corresponding to this x to the k minus 1. And then we just have a complex we have this exponential function, and the rest is all in this normalization amplitude factor A. And what you can control the filter order by k, and you can control the bandwidth with the factor b, because the smaller the factor is, the more slowly the function goes up and down, let's say. That means that the more it's stretched in time. And then this would be kind of this gamma function, or gamma distribution function. And this is then multiplied with a cosine term. And you can select a phase term, but most important is that there's a center frequency. And if you have a relatively smooth function here, this would be more or less as the frequency response would have a low pass characteristic. And if you multiply a filter with a cosine, such a low pass filter with a cosine function, it's a kind of modulation by multiplying an impulse response with a cosine function. This is in frequency domain, a shifting to positive and negative frequencies, because cosine has a positive and a negative frequency component in complex frequencies, in the complex domain, let's say. And that's why you get then a bandpass filter. You make out of this Fourier transform, let's say, of this function, this would be shifted so that its center ends up at f0. And this is then the impulse response of a time continuous gamma tone filter. And you can select, as we said before, you have to select the center frequency and the bandwidth parameter so that they match the properties which you want. And this would be then corresponding to the Bach scale, ideally. And if we want then to approximate this with time discrete filters, we can't use the same order as this is here, just the exponent here. This is not connected to any filter structure order. So, but if you implement that and approximate that with an IIR filter, you would select the proper parameters and the proper frequency, proper filter order with a number of poles and zeros and so on. So and normally this is approximated with 8th order IIR filters. And then from that, you can find in the literature, which I also will give you, and also in the examples I will show you. Then I will do that next time with some software. You can see how you could calculate the parameters of those filters, of those IIR filters from the desired center frequencies and the desired bandwidth, let's say. Then some people don't use use IIR filters with in this case they could have 8 poles and 8 zeros. It's a full-blown 8th order IIR filter. Did you have all the classes on digital signal processing? Yeah, so that should be quite clear then. So some people use so-called all-pole filters. That means they just the numerator of that transfer function would be just constant, and then you would get a somewhat simpler implementation, or you could have some other advantages of that. And this has then a slightly reduced DC suppression, and we will see examples now. So this term all-pole gamma tone filters will come sometimes, and the other things I will explain. And then one thing is we have quite narrow filters if we want to cover the whole frequency range up to 20 kilohertz with our gamma tone filter bank. We need a sampling frequency which is at least 40 kilohertz from Nyquist theorem. And if we would then have filters with a bandwidth of 100 hertz would be the critical bandwidth. But if you remember the Bach scale, it went down to below 50 hertz. You have a filter with 50 hertz bandwidth and at a sampling frequency of 40, for example, 48 kilohertz for audio signals. Then there's so narrow that the poles here, these poles are moving very close to the unit circle, and by rounding errors, even in double precision, you can get instabilities if you implement them as the direct form of an 8th order IIR filter, which would be the most straightforward thing to do. But if you want to avoid these instabilities, you can do better by implementing the whole filter bank as a cascade of 4 2nd order stages instead of 1 8th order stage. I will explain and show you too as well how this can be done and give you examples. But this would now be the frequency responses, which are where you can find the recipes for how to design them. These are not all gamma tone filters of the filter bank, because you would have quite large gaps in between. This is just a sub-selection or a selection of a subset of filters, just showing the general characteristics of the filters. And you see that the bandpass characteristic, that they're relatively steep, so that the attenuation here is 0 dB. They're all normalized that they're at 1. That means it's magnitude response at center frequency is 1, so that would be 0 dB attenuation, and then it goes down quickly to relatively high attenuations. So this would be one set of approximated gamma tone filters. And if you compare that with all-pole gamma tone filters, you would mainly have to look what's happening here around 0, around frequency 0. But you see here that the first filter goes down quite steeply. It goes to something like almost 60 dB. Now, if we look at the all-pole gamma tone filter bank, you see that the attenuation at 0 is quite a bit less. So that's then the kind of a disadvantage of the all-pole gamma tone filters in comparison to the normal gamma tone filters. And so you can also look at the impulse responses when you design these filters. And this is just one plot we don't have the correct y-axis, because the y-axis for plotting impulse responses should be the value of the impulse response. But here they introduced also the center frequency, because so the numbers here show the center frequencies, and the actual amplitudes are not shown in numbers here. So you can just see the shape of the impulse responses, and you see that would be the filter corresponding to 400 Hertz center frequency, and so on. And this would be the filter corresponding to 10 kilohertz center frequency. And what you can observe is, first of all, that of course this modulation must be slower for a 400 Hertz center frequency. So this should be a 400 Hertz cosine function, which was multiplied with this envelope. And if you have a 10 kilohertz center frequency, this should be a 10 kilohertz cosine function multiplied with the envelope. And another thing you can see is, if you want to have quite a narrow filter, a narrow bandpass filter, the impulse response must get quite long. If you want to have a good frequency analysis with a high resolution, you need enough time, measurement time, to get that good frequency resolution. So this is this kind of time bandwidth uncertainty, you can say. Normally you have time and space uncertainty, but here we have kind of time and frequency uncertainty. Means if you want to have a narrow filter, you need quite a long impulse response. And if you have a high bandwidth, and at high frequencies we want to have high bandwidth according to that ERB, and there we can have the impulse responses are very short. Of course, they're all infinitely long because it's all IIR filters, but they decay much faster here than here. And that would then be one thing which ideally matches with the auditory system, and that can be proven that the auditory system also has this property that it has higher temporal resolution at high frequencies, where it has lower frequency resolution, and it has lower temporal resolution where it has high frequency resolution at the lower frequencies. So that we have that match, and that's why the gamma tone filter banks are quite a relatively good first approximation, let's say linear approximation of what goes on in the cochlea. And that's why they're used so frequently. And maybe next one, and then maybe I should stop. I can already point you to some things you can find in the internet. In MATLAB, you have different toolboxes and codes, and I have experimented with the code and added something to find out, for example, also to show the stability problems and so on. Then you can find different gamma tone, different Python implementations, and I think it's not yet on Studon because I just made it this year newly, my own Python code for gamma tone filter bank implementation, which you can then freely use and experiment with it, and which I already had the years before, is some C code for implementing gamma tone filters. And then of course the gamma tone filters or the implementations in C are the fastest, and Python is also quite efficient if you use the corresponding libraries, and MATLAB is quite okay, but Python is also quite good what you can do. So I will show that next.